Okay, I'd like to welcome everybody to Lecture 13 of CSE 548, the analysis of algorithms. Are there any questions to start off about either the programming assignment, which is the competition which is starting, or about the graduate projects? I passed out the graduate project sheet last time, or anything else bureaucratic to start off with. Question? Yes.
Are we allowed to assume there are no parallel edges?
Okay, on the question was about, are we allowed to have parallel or multi-edges in the graph? Presumably you mean, is it possible to have two edges between a particular pair of vertices? The answer is you should not see them in the data file, but they shouldn't cause you any trouble as far as the bandwidth goes, because the bandwidth, remember, was going to measure the length of the longest edge. If there's two edges of the same length, it doesn't cost you any more than having one edge of the same length. So it shouldn't phase you even if it was there, although I don't think they'll be there. Okay, any other questions? Okay, now I have the data files on the World Wide Web. You can get them from the web page. There's one file, you can click them one at a time, or there's one file I have called all files, that if you click on that one, will get you a char file with all the files on there, so you don't have to click a lot of buttons. Okay. Has anybody successfully retrieved the data from the data files? Okay, so it is definitely possible. Question? Okay. Char file, if you have a char file, what it says is some instructions at the top of the char file that say delete everything else and run it through the shell program, /bin/csh. Okay? So follow the instructions that it says at the top of that file to delete the header, and then run that whole thing as a shell program through /bin/csh. And that should do it. Okay? Any other questions? Okay? Very good. Has anybody actually got a program that's starting to work at all? Okay? How big a problem can you solve? Just a quick question.
11, 12.
Up to 11 or 12. Okay. Not bad, but we can do much better than that. Okay, so 11 or 12 is now the target that people are trying to hit, but I don't expect that record to last very long. Okay, it's a good start. Okay, has anybody got anything faster than 11 or 12 now? Okay, so the race is on. Now 11 or 12 is what it'll take to be the leader. Okay. Anything else? Any other questions? Okay, last class we were in the middle of trying to do starting dynamic programming. Okay, and we started going through the first sort of real example, which was matrix, trying to find the best way to multiply matrices. But the problem of the day asks for a dynamic programming for a different algorithm for a slightly different problem. I'll go over the problem of the day, and then and then we'll continue back with what we were doing. The day asked, give an order n² algorithm to find the monotonically longest increasing sequence in a sequence of n numbers. Okay? Now, what does that mean is the first thing that you should be asking yourself when you want to look at this question. Okay? And my initial reaction is I build an example. Okay? Here's an example sequence for 4, 5, 5, 2, 8, 7, 1, 6, 4. Okay? What do we mean by monotonically increasing? We mean that each element in the sequence that we're looking at, okay, is longer, has a value greater than that of the previous one. So what would the longest increasing monotonic sequence be for this particular example? Okay. Any ideas? 2. Well, 2. What would 2 be? Some people say, well, 2. You could have 1 and 6. Okay. The other thing is that there's nothing here that says that, and this is maybe the tricky part, nothing here that says that this sequence is connected. Okay? So some people say, well, look, 2 and 6 is the longest one. What if we're looking for the longest scattered one? Okay? Where we could, in fact, have a slightly larger one, I believe. Okay? We could say that, actually, could we say? No, we couldn't say.
You couldn't say anything.
Okay? Suppose we had a 3 in here. Okay? Then we could say a lot. Okay? Now, suppose we had a 3 in this example. Okay? So this is a 3. I'm sorry. Now it's 5, 2, 8, 7, 3. Now what's the longest increasing sequence? Okay? We could go from a 2 to a 3 to a 4. Okay? And skip numbers and come to a larger one. Okay? So what the problem was really asking, and where, let's say, dynamic programming is really useful, is going to be in finding the one where you're allowed to skip elements. First, could anybody give me an algorithm just to find the longest increasing sequence in where you're not allowed to skip elements? Okay? Order n. How would you do it in order n?
Just scan through the list, see if the next number is greater than the previous. If it is, increment some counter.
Right. So if you wanted to just find the longest consecutive sequence of runs, that becomes fairly easy. You could sort of think, well, I'll scan from left to right, and I'll put a divider every time the numbers, let's say, decrease. Okay? When there's a local change. And finding the largest gap between consecutive numbers could then be found by saying, what's the largest gap between these parentheses, or these dividers? So consecutive is easier. That's linear. The hard one is the fact when you're allowed to skip elements. Okay? How do you figure out which is the right subset of things to skip? Okay? Now, the way that you would use something like this, try to solve this in dynamic programming, when I try to formulate a dynamic programming algorithm, what I usually ask myself is, what would I like to know about the first n-1 elements, such that I could use that information to figure out what's this ultimate answer for all n elements? Okay? So what would I like to know about the longest increasing sequences? Okay? One thing I'd like to know is what is the length of the longest increasing sequence in the, among the first n-1 elements. Okay? Obviously, that might still be the longest increasing subsequence when I put an extra element on. Okay? Namely, if I delete the last one, you tell me what the longest one you found so far. That I'd like to know. But what else would I like to know when I add that extra element back? I want to know what sequences can this thing be stuck on? Okay? Because there's a chance that by adding this last element, okay, it's going to be able to extend something else. So what I claim that I'd like to know is, the thing that I want to know is what's the length of the longest sequence that I can extend by adding the last element. Okay? And for that, what I really think I'd like to know is, for every element in my permutation so far, okay, I'd like to know what is the length of the longest sequence that ends at that element. Why is that? What do I know about, if I'm going to add a number 4, so let's think, what's the length of the longest sequence that ends in 5? It's going to be 1. That ends in 2, it's going to be length 1. Longest sequence that ends here, well, it's 1 more than the sequence that ends at 5, correct? Or 1 more than the sequence that ends at 2. So there's a sequence of length 2 that can be made here. What's the longest sequence that ends at 7? Well, it's 1 more than this or this. Why is it 1 more than this or this? Why can we extend 7 to the end of either the sequence that ends in 5 or the sequence that ends in 2? Because 5 and 2 are less than 7. We can't extend the 7 after the 8 because it's bigger. Okay? What's the longest sequence that will end in 3? Well, it's 1 more than the length of the longest sequence that ends with something smaller than it. Okay? Which is 2. Longest sequence that ends in 1, well, nothing is smaller than 1. So it's 1 plus nothing. 6, well, it's 1 more than the length of the longest sequence that's less than that. Which is the longest such sequence? Well, 3 is less than 6, okay? And that's the largest such thing, so 2 plus 1 gives me that. The claim that what I really want to know at the end of each round is, what is the length of the longest sequence that ends at each character? Okay? And once I know that, then I can solve my problem. Okay? I can talk about a recurrence where the length of the longest sequence that ends in the ith element is the max over all values less than I, okay, meaning all the elements to the left of it, okay, plus all elements that are actually less than the ith element, If you've got a big sequence that ends with a number bigger than me, I don't care about it. Okay? I'm going to want to maximize over all possibilities. Okay? For each one of those, I'm going to take their length and add 1 to it. And I want the length that the longest sequence ending in the ith element is 1 plus the length of the longest sequence ending before it that's less than it. Okay? So this is my recurrence relation. Okay? What is dynamic programming? It is a way of computing a recurrence relation efficiently by storing partial results. What is the partial results that I'm storing? Value of s sub I, s sub 1, s sub 2, s sub 3. So what's the time for this algorithm? How many boxes will I have to fill in for when I compute up to an n-element permutation? How many boxes? N boxes. How many things will I have to look at to fill up the ith box? Okay. I'll have to look at most I numbers. All numbers less than that. The biggest I can get is n. I've got n steps where each step involves looking at most n boxes and picking the largest of the bunch. N times n is n squared. That gives me the bound that I was looking for. Okay? And what was the point of this thing? I really wanted to figure out what was the longest sequence overall. The longest sequence overall is going to be, it's going to have to end someplace. Okay? So why don't I, at the end of it, say, why don't I maximize over all s sub I at the end? If I know the length of the longest sequence ending in each position, the maximum sequence overall is the one that ends up in the, that is the largest that ends in each position, or by maximizing the values of s sub I for all values from 1 to n. Okay? Any questions about this problem? Okay, yes?
Would it help anything if you would sort those which you had already computed?
Okay, so the question is, would it help any to sort those that I've already computed? So one thing with what you're saying is that, in fact, maybe I don't need...
if you set whatever the 4 at the end, you only have to look at 1, 2, and 3. All the higher ones you don't have to really look at.
Right. So the truth actually is that by using fancy data structure, okay, using a data structure in a clever way, you can actually get this time down to n log n. Okay, it's not just sorting. Okay, it's something a little bit. Basically, you have to maintain a search tree with the right keys in it. Okay, but in fact, you can do it faster. Okay, but that I don't want people to worry right now. The key thing to see is to understand the dynamic programming idea. In fact, the faster algorithm is still using the dynamic programming idea, but just one other idea to make it even faster. Okay? The key thing is to see where the n squared comes from. Okay? Any questions about that? How many people see it? Raise your hand. How many people don't see it? Okay? A couple people. Okay? Well, let's go back to the problem we were looking at last time, just to make sure that we see where the recurrence comes from. That's the first step in any dynamic programming problem. This should look familiar. It's just what we were last time. We'd agreed that we wanted to multiply a chain of matrices. We agreed that we had the flexibility to stick a, basically to stick a, to parenthesize the expression as we wished, okay, without rearranging the terms, okay. How did we find the cheapest way to do it? Okay. My claim was that a correct recurrence relation to compute the optimal matrix product, cheapest way to compute it, is that for the run of matrices from I to j, we have n matrices, matrix 1, matrix 2, matrix ... matrix n, okay? To compute the cost of multiplying the ith through the jth matrix, what we know is that somewhere between I and j, there's going to have to be an outermost multiplication sign. Okay? That whenever you do a parenthesization, there's going to be an outermost parenthesization. Here is the outermost one here. Correct? Okay? That outermost parenthesization, to do you any good, that actual multiplication sign is going to have to be between two of the matrices. Doesn't do you any good to put the matrix multiplication in the next counting. Okay? You're looking to stick multiplication signs, parenthesize things between your matrices. So there's going to be a spot between I and j minus 1, okay? Basically between all the possible gaps between the matrices. Okay? What is the cost going to be? Suppose we decide to put our outer parenthesis here. What is the cost of it going to be? It's the cost of multiplying the matrices from I to k. If this was the kth spot, the cost of multiplying from I to k plus the cost of multiplying from k, basically past k, the k plus first matrix, to j, plus the cost of that outermost multiplication. What was that outermost multiplication? We're multiplying this by this matrix by this matrix. So the cost is you go from the I minus first boundary times the cost of the middle size times the cost of the last size. Okay? This, I claim, has to be the best way to multiply the matrices. Okay? You know that any way you multiply it, there's got to be an outermost thing. That outermost thing has to be someplace. I am picking the outermost thing such that it minimizes this quantity. This quantity is exactly the cost. This has to describe the optimal way to do it. Okay? Any questions about why this recurrence is correct? That's the important thing to see right now. Okay? Good. So, how much time does it take to actually evaluate this recurrence relation? Okay? What we're really interested in is the cost of multiplying matrix 1 to matrix n. So there's n matrices. How many different values of I and j are possible? Okay? The left coordinate is going to be somewhere between 1 and n. The right coordinate is going to be somewhere between 1 and n. Look what's happening. We start out calling, what is the cheapest way to multiply from 1 to n? It's going to make up smaller values. Well, what's the cheapest way from 1 to 2 and from 3 to n? From 1 to 3 and 4 to n. Okay? But there's going to be at most, in fact, there's going to be exactly n squared different values of this matrix. Okay? N squared different values of this recurrence. How much time does it take to evaluate each one of these things? How much time does it take to evaluate the value of m sub ij? Okay? What's it got to do? Okay? It's going to be taking the minimum over all k values in between. How many different values are there here? J minus 1, or at most n, because the difference between 1 and n is the biggest possible thing. How much time does it take to look up a value in a matrix? One step, order 1. Order 1. Multiply 3 numbers together, order 1. What is the time it takes to fill in each cell? Order n. So you've got n squared cells, each one of which takes at most order n time. Total time is n cubed. Okay? And we find what has to be the best possible ordering. Okay? Any questions about that? Okay? Now there are a couple of subtleties here that need to be sort of seen. Okay? First thing is, what are we really doing in evaluating these matrices? Okay? I mean, there's a couple different ways of looking at it. If you at first you call matrix 1 to n, it's going to ask you for 2 of n. That doesn't already exist. If you start first calling it from with the big values. The right way to evaluate this recurrence is to evaluate it from the small values up. So what I would do when I think about how this computation is really working is think about a matrix, okay, a matrix where we're storing all the possible solutions. Okay? This is the optimal cost of computing from I to j. Here, that's the I-axis. Here's the j-axis. Okay? What's going on? What's the cheapest way to multiply from matrix 1 to matrix 1? Okay? How much work do you have to do to multiply one matrix? Nothing. So the way to interpret that is that this costs nothing down the main diagonal. That's the basis case for our recurrence. What if we now want to figure out what's the cost of multiplying matrix I to matrix I plus 1? Okay? That is going to correspond to the points right above the diagonal. If you think about this matrix, we are going to have a diagonal that's going to be cruising up as we get more and more complicated. For each one, what we're going to be doing is sticking our, we now have a gap. The difference between I and j is going to be define which diagonal we're at. So when we go from I to I, that's the 0th diagonal. I to I plus 1, that's the first diagonal, second diagonal, third diagonal, dot, dot, dot. What's the point here? If you go to our recurrence relation, if we go between j and I, we're going to pick some k value that's between that. That means that the distance from I to k is less than the value from I to j, correct? And the distance from k to j is less than the distance from I to j, correct? So if we've evaluated all the smaller cases, in evaluating ij, we know that those smaller cases are going to have to be sitting there waiting for us when we need them. So if we evaluate this recurrence relation by starting with the small values, okay, and working up, the values that we want to have stored in this matrix will have already been computed, and they're sitting there waiting comfortably for us. Okay? That's the idea that we're going to need in computing this thing. So the algorithm that we're going to use, if you want to look at a code here, here's a pseudo code for how we're going to actually compute this recurrence relation. Okay? We're going to have a loop that runs from each diagonal. Okay? There's going to be a diagonal that's going to represent the difference from I to j. Okay? Starts out at 0, 0. Those are all going to be 0. Then the difference is 1, 2, dot, dot, dot. Then for every value of I which is possible, pick the value of j that is I plus that diagonal element, so that that's the gap between the two of them. Okay? Now we've got our I and j values. For each one of these, we're now going to loop through all possible values of k between I and j. And know that since the difference between these two has been computed, it's going to be sitting comfortably in the matrix, and we just read it. Okay? This is how we get an n-cubed algorithm for solving this thing. Okay? It's important not to lose sight of the mystery. Okay? We had a recurrence relation. That recurrence relation was abstract. But looking at the recurrence relation, you should see that it's possible to evaluate it in n-cubed time. The next step is simply to sort of go and order the way you fill in the slots so that everything is waiting when you need it. Okay, any questions about that? Okay, question.
What would be so bad if you just do it recursively?
Another way of doing it, okay, would be that you could think of doing this all as recursively, and whenever you have a value, fill in the matrix and mark that you filled in the matrix so you know that it's there and not junk. Okay, there's a technique called memoization, which I think is described in the book, that basically works by doing a depth-first search instead of figuring out the evaluation order. Okay? The trouble is actually that's actually sometimes a very good way to do it. Okay? The trouble is it involves being a little bit, it involves doing a certain kind of programming that's different than working out the ordering. So the bottom line is that's not necessarily a bad way to do it. But to make sure that you really understand what dynamic programming is and why it's working and why it's magic, you have to see that you can fill in the order such that everything is there that you need it. Okay, so that's why I'm going to talk about this as opposed to memoization. Okay? Because once you see why it's done, then it just sort of says, well, it's obvious. Okay, and then you can sort of do that. Okay, any other questions? Yes?
The first line of the code should be initialized at that diagonal.
Right. So you're saying this should be M sub II. Okay, well, that was M sub II. You just couldn't see it properly from where you were sitting. Okay, now it's right. Okay, any other questions? Okay. Now, there's one other mystery about what we're doing. First of all, how many people think they understand what's going on so far? How many people are a little confused? Okay, a bunch of people. Okay. One other thing that might be confusing you, if you stop to think about it, is all that I'm returning to you is the cost. Okay, let's just think about what's actually happening here. Okay, let's go through the actual evaluation. This you're not going to like because it's my hand drawing. But basically, what's going to be happening when we evaluate this recurrence relation? Okay? What is the value of this cell? Okay, again, this is going to be plotting the cost of I to j. So each box here is going to be the cost of multiplying matrix I through j. Now, in between each I and j, in between each matrix, is in some sense a shared dimension. Okay, so the way that I think about what's actually happening here is that we've got a, let's just maybe make it larger. There's a boundary of the matrix that's going to be the same here. That's the P sub I here. But what's this thing? The cost of multiplying the ith matrix to the ith matrix is always 0. So we set that matrix 0. What's the cheapest way to multiply from the first matrix to the second matrix? Okay. Suppose I give you two matrices. Okay, let's say I give you a working pen. Sorry if you can't read that very well. Suppose I give you two matrices. What's the optimal place to stick the parenthesis? Or stick the outmost multiplication sign? Between them, you have no choice. Okay, so that's not a hard question. Okay? The cost of multiplying from matrix 1 to matrix 2 is the product of the size of the dimensions. So if you go up here, the cost is simply going to be the product of the dimensions. It's a 30 by 1 by a 1 by 40 matrix. That's the cost to multiply from I to j, from 1 to 2, correct? What's the cost of multiplying from 2 to 3? Well, it's simply a function of the dimensions. Okay? What's the cost of multiplying from 3 to 4? Simply a function of the dimensions. There's been nothing interesting that happens yet. Where something interesting happens is what if we have 3 multiplication matrices to multiply? Where does the outermost multiplication sign go? Okay, it can either go here or it can go there. Is there any other place where it can go? Can't go. What's it going to cost us if we put it out here? Well, that meant that we multiplied these two together and then multiplied the product by that, correct? So what's happening in that cell? We're going to say here that the two possibilities, the outermost multiplication sign could have been between 1 and 2 and 3, or between, it could be basically between 1 and 2, or it could be between 2 and 3. What's the cost of the possibilities? Well, it's the cost of creating mi plus that, the cost of creating that, plus the cost of multiplying the two resulting matrices, or it's the cost of doing it the other way. Okay? Namely, there's going to be, once we stick that parenthesis in, there's going to be a different set of terms on the boundary. So the resulting matrix is going to be a different size and a different cost. And we're adding up different subproducts. We had to make the matrices we're going to use if the outermost multiplication sign was there. So which is the best way to multiply three matrices together? It's going to be the minimum of the two possibilities. Either we do 1, 2, 3. Either we're going to do it like this, or we're going to do it like that. Okay? And we're going to pick the better of the two, the cheaper of the two. In order to do that efficiently, we need to know how much this is going to cost. But we know how much that costs because we already looked it up. Okay? That's why we get this cell. Okay? And likewise, if we cruise down the diagonal again, we have a similar cell where, again, we're taking the minimum of two possibilities. That and that. Okay? What happens in the third diagonal? Now we've got four matrices to deal with. How many possibilities are there for putting the parentheses in between? There's three possibilities for the outermost multiplication. So what's actually happening in that cell? We're taking the minimum of three possibilities. 1, 2, 3. For each one, it's going to be the cost of two cells in the matrix plus the cost of the outermost multiplication. We pick the smallest of the three. That's the cheapest one. That's what we do. That's what's happening. Okay? Any questions about the order of the evaluation, what we're actually doing? Okay, there's two separate things to understand. One is, why is the recurrence right? And the second is, how do you fill it in? Okay? If you don't understand one of those two, ask. Okay? And we will deliver. Yes?
Can I say each step we use gradient?
Okay? At each step, what we're doing is we're picking the best possibility of the three. Now, why are we picking the best one of the three? That's really what is an interesting question. Okay? We know that once we've decided to multiply a rung of matrices together, can't see. Okay? Once we probably let me shrink this thing. We know that once we've got a run of matrices together, once we decide to set the outermost multiplication sign here, there might be a lot of different ways we could parenthesize this. Correct? Is there any reason why we're not going to want the best one for this? Okay? If we pick two different ways of parenthesizing it, we get exactly the same answer as the actual value of the product. Whichever way we decide to do it in here has no impact on the correctness or the time it takes to multiply outside that bound. So that's why we're going to pick the best of the three. Because it's basically saying we're going to want to buy the solution of that run of matrices. We want the cheapest way to do it. That's why we take them in. Okay? That has to be correct. Okay, any other questions? Okay? There's one other issue that comes up in this thing. Okay? I have shown to you how to compute the cost of the cheapest way to multiply the matrices together. Okay? That you should believe from the recurrence relation. But from these numbers, can you figure out what the real parenthesization actually was? Okay? No, not really. Okay? Or, in some sense, all that you know here is, look, the last thing I did, the cheapest way to multiply all the matrices cost me 1,400 steps. What you're really interested in not only knowing what the cheapest way is, but you'd also like to know what is the actual place where the multiplication sign took place. How could we figure out what that actually was? Okay? There are there's two different ways. The simplest way is at each step to store what was the way that I did it. think about what I was doing here. Okay, I picked the cheapest of 3 options. Why did I pick what did it mean to pick the cheapest of 3 options? Each one of these options was defined by a different place to put that last outermost multiplication. Correct? Why don't I instead store a table also where once I figure which was the multiplication that I chose, why don't I store that position in my table? Saying if you want to know what was the cheapest way to get this value, I picked the min of 3 here. That was the first possibility, it turned out. So let me store here, hey, the actual thing that I chose here for my outermost multiplication was the first spot. That then divided my problem into 2 pieces. Okay? And if for each point I stored the decision that I made of where that outermost multiplication should go, I can then work backwards and read out where those parentheses should have gone. Okay? And from that, reconstruct the order that I had. Okay? This is another thing people find confusing about dynamic programming. The bulk of work that I'm doing is computing what the cheapest one is, what the cost of it is. But ultimately, you don't just want to know the cost, you want to actually get the object you're buying. Okay? And so what you need to do is to store, keep track of what decisions you made to get to where you were to reconstruct that. Okay? Any questions? I see a lot of stony faces out there. Okay? Question?
Could you explain how you resolve
How do I do the work backwards? Okay? What did I actually store in each value of this supplementary array? What was the cheapest? Where did I put the multiplication sign when I was multiplying matrix? I had 1 matrix in my chain. Nowhere, so I don't have anything on that diagonal. Where did I decide to put the multiplication sign where I was multiplying between matrix 1 and matrix 2? I didn't have any real choice. I put it between there. Between matrix 2 and matrix 3, I didn't have any choice. I put it there. Between matrix 3 and 4, I didn't have any choice. I put it there. The next case, I kept up and said, where did I put the outermost multiplication? I stored which of my possibilities did I choose to actually derive the min. That's what I stored in each cell. Now let's work backwards. What did I know here? I look at this ultimate top cell. It says in the optimal way to multiply all the matrices together, the outermost multiplication was between 1 and 2. Correct? That's what this is really saying. What do I now know? On the left-hand side, I'm going to have to, now I have a matrix between 1 and 1. What's the optimal place to put the next most parenthesization in there? Well, it's between 1 and 1, 1 and 1. There is nothing between 1 and 1. The more interesting side is the right side. So I put my parentheses around it. And now say, what was the optimal way to multiply between 2 and 3? Well, look that thing up. Between 2 and 3, the optimal outermost parenthesis, that would be on the second one,
2 and 4.
Between 2 and 4, well, wait, no. Okay, if I take a look at what did I actually do here, my claim is that now I've got between 2 and 4. You're 100% right. 2 and 4, that's this cell. That tells me that the next multiplication had to take a spot at the third spot. And that now broke this into 2 more subproblems. What was the optimal way between 2 and 3? Well, that was at the second spot, which is there. What was the optimal way between 3 and 3? It was, well, in the third spot. It was a trivial case. Okay? So we can actually reconstruct that with a simple recursive kind of an algorithm. Okay? What's the optimal way to multiply matrices from I to j? Well, we are going to, basically, figure out where was the outermost multiplication sign, write this is a parenthesis, Okay? Order, come up with what was the right ordering for everything to the left of it. Output the multiplication sign. Then find the right order of everything to the right of it. And output another parenthesis sign. This is how we basically go back and read it. Okay? It's straightforward once you sort of understand it. Okay? It's a little tricky, but I mean the basic idea should be clear. We're just going back and reversing the decisions we made before. Okay? Since we stored those decisions, we can reverse them. That's the idea. Okay? Any questions about that? Okay? Let me try another example. Okay? But again, before we see the example, think about what dynamic, know what to look for when you see examples.
Just
Yeah.
looking up of the reverse of the decisions only takes order n.
Right, the time to look it up is basically reverses the step that you're doing. It should happen in linear time. Okay? Certainly it shouldn't be surprising that the time it takes to look up the right solutions is less than the time to compute it. So, or no more. So what do we have when we have a dynamic programming algorithm? There's three things to look for. Okay, and this is what you should notice every time we do it. First, you formulate your problem as a recurrence relation. Try to figure out how do I get the answer given, what do I need to get the answer from my previous stuff in order to get the answer with adding the next element. I show that there's not too many of those possibilities, so I can store them all comfortably. And then I order the way that I evaluate it, so that I know that whenever I need something, it's there. Those are the three components to what we're doing. Okay? What's another example? Well, a famous application of dynamic programming has to do with approximate string matching. How many of you have ever used a spelling checker? Okay? Well, a lot of people. Okay? Now, some spelling checkers, good spelling checkers, will not only tell you that your name is wrong, your word is spelled wrong, it will suggest a substitute. Now, how does it suggest what substitute? Okay? A bad idea would be to pick a word from the dictionary at random. Okay? That obviously isn't good. Okay? You want to pick a word from the dictionary that's close to what you're looking for. Okay? You'd like to know that when you type out the word misspelled, okay, that, well, if you look at it, the difference between the way I spelled misspelled and the way real people misspelled was just that it was sort of, I left out an S. Okay? So you'd like to try to figure out, for all the words in the dictionary, which word is closest to the one that you typed. Okay? What does closest actually mean? Well, closest means that you could have made three kinds of errors. One kind of error you could have done is substitute a letter. Okay? Like when you spell cat, you may have said, well, cat, K-A-T. No, it's wrong because, in fact, it's really a C instead of a K. Okay? That's a common kind of an error. If you make one substitution or so, you'd like to be able to detect that. Another possibility is that you add a letter to your text, to your word that shouldn't be there. Okay? Like, you know, fairly often you don't know if you have one L or two L's when you would put things together. Okay? So maybe you add an extra word, character. Or, as in the case of my word misspelled up here, I could have been missing one word. So the three kinds of operations that it seems to me that you can do in misspelling a word, or in modifying one word and finding somebody close to it, is you could change a character, you could insert a character, or you could delete a character. Okay? Which word would you like your spelling checker to give you as a suggestion? Okay, of all the words in the dictionary. Okay? Seems to me the natural choice is the word which requires the fewest number of changes between what you gave and that word in the dictionary. Okay? If you can say, look, misspelled, all I have to do is change that one S, and now it's a real word, and every other word required more than one change, you know misspelled is probably, you know how to correct it. So in general, I claim that what we want to do is take as input a text string, and as input a pattern string, and find what is the smallest number of insertions, deletions, and substitutions we need to do to convert one to the other. Okay? That is what we mean by approximate string matching. Okay, any questions? Okay? So let's look at an example, just quickly. My claim is, and let's just confirm this thing, that by doing the right 3 edit steps, we can convert this string to another string. Okay, so unnecessarily, which is really spelled badly, to what it should be spelled. What would be the right thing to do? One idea would be, well, we could delete this n. Okay. Another idea would be that we could substitute this. And a third would be that we insert this. By doing these 3 operations, we can convert this string to that string. Okay? And in fact, there is no cheaper way to do it. Okay? If we consider we pay a cost of 1 for every one of these operations. Okay? So the hard part is, now, how do we find that these are the right things to do? Okay? You might say, well, match them from left to right, and when you see a difference, just delete the character, or change it, or something like that. Well, you don't know that the local change you make is necessarily the best possible change. Question?
Just assume that P is very close, but not quite the same as T.
Well, the question is how small is P and T? How small is the change? Well, it depends upon the application. For spelling checking, it's probably pretty small. You'd like to say that if somebody's made 4 or 5 errors in a particular word, odds are you can't expect them to correct it. Okay, if they type the word in Greek, let's say, you can't expect them to fix that up. But in a lot of other applications, like in biological applications, okay, where you want to compare one one DNA sequence to another, there can be lots and lots of error changes that you need to make between one and the other. Right. So if, let's say you wanted to figure out, you have a gene, let's say, for hemoglobin, and it's a hemoglobin in people, and you've got a gene for a rat. You'd like to figure out, is that rat gene close to the hemoglobin gene? Is that the rat gene for hemoglobin? Well, we're different from rats in some ways, okay? And so there's been some changes, okay? Potentially a lot of changes. So in general, there might be an arbitrary number of deletions, substitutions, and insertions necessary, okay? So we have to be able to handle large numbers of changes in the real problem.
But in the spell checking problem, they're only a small number.
In the spell checking problem, you're saying there might not be too many of them, okay? But what if, let's say, you were doing a database search, where let's say there were, the point is, okay, in a spelling application, you probably won't have too many errors, as I agree. Okay, in other applications, it's important to handle large numbers of errors. So we're not going to worry about how to try to do it in the case of 1 or 2 errors. We're going to try to figure out what's the minimum number of errors we need to make. Correct. Okay? Any questions about that? Okay?
Transpositions are handled as substitutions?
Then there's other possibilities. You might say, well, a lot of errors are sort of typing problems, that maybe somebody, you hit your fingers in the wrong order. And so maybe it should cost less to, you could, if I type A, B, B, A, I could change this to this by doing 2 substitutions, or by doing 1 transposition. I could say, hey, just switch them around. Okay, so that could be another way of defining it. Turns out just about any way you want to modify this problem, okay, maybe making certain errors more expensive than others. All of those can be handled by basically modifying the simple dynamic programming algorithm. Okay? So that's why I don't want to complicate things. We only have 3 kinds of operations. Okay? Namely, we can insert, delete, or substitute. Okay? So what's the cost of editing one string to another string? Okay? I say let's model it as the following kind of a recurrence relation. Let's let d sub ij equal the minimum number of differences between the first I characters of the text and depending upon what you want to do, first I characters of the pattern and the text ending in J. Okay? I give this a symmetry. The reason why I don't say the text from 1 to J is maybe you've got a situation where you have a long string and you're looking for a particular misspelled word in there. You want to try to find the best possible match to something in the dictionary, but you don't want to go back to the beginning because maybe you've got more than one word adjacent. Okay, so that's why it's a little bit asymmetrical, but that shouldn't be too confusing. I claim that what I'm interested in is the minimum number of differences between the first I characters of the pattern and basically the first J characters of the text. Okay? What is that going to be? Well, it depends upon what are the possible last things. Sometimes, how do I design these kind of programs? I say, what information would I like to know to compute this cost? Okay? And what would I like to know about this cost? It seems to me that if I was matching a string to my text, and that's the ith position, that's the jth position, I know that I did something right before it. What are the possibilities for the last operation that I did? I could, if I was aligning the string ABC and BCC, if this is where I and J end, if they matched, the cost of doing that would have been the cost of matching up to here plus nothing because we did a match. If instead these were different characters, it would be the cost of matching up to here plus 1 for doing the substitution. So one possible way to match them is to say if the ith character is equal to the jth character of the text, okay, then we pay the cost that we would have paid to get to the pattern and text by deleting both the last of character of each. If, on the other hand, they were different, we could have done a substitution, which would have cost us what we cost to get there plus 1. Okay? So the one option we have is we could do a substitution or a match. Another option we could do is to delete something from the text. Correct? So if we had deleted something from the text, what would have happened? Okay? We want the match, okay, that where we find, if we're deleting a character from the text, we want to know what's the optimal way to match the first, okay. Whether we do the insertion or deletion gets a little bit, they're sort of symmetrical cases. In one case, we're going to want to know what's the best possible way to match the first I-1 characters of the pattern against the text so far. That's in the case where, let's say, we're going to delete one of the characters from, maybe I'm a little confused. I think we delete the character from the pattern. Otherwise, we'll advance the other pointer. Okay, if we delete a character from the text, we move one pointer up and not the other. Okay? Depending upon which one we want to delete. Suppose, let's say, we have a string ABC, AB. Okay? Let's say AB, and this is what we've, let's say we have XAB. Let's make XAB. Okay? We want to now say, what are our options here? We could match B and C, but no, they don't match. Okay? So in that case, what we could pay the cost of a substitution. Or we could say, let's delete that last character and figure out what was the cost of matching the first I-1 characters with the J characters here. Okay. Pay the cost of that, pay the cost of the deletion, And that's the cost of actually editing it to this. So the cost of editing from I to j could be, figure out the cost that it would have been if that last character didn't exist in the text, and then pay 1 for the cost of deleting it. Or say that that character did not exist in the pattern, and pay 1 for the cost of deleting it. Okay? There are 3 possibilities. We could either end by doing a deletion, we could end by doing an insertion, or we could end by doing a substitute or match. What we're going to want to do is the cost of editing from I to j is going to be the best of those 3 possibilities. So we are going to want to take the minimum of these 3 options to fill that particular cell. Question?
For a dictionary or for spell checking applications, isn't it an implicit assumption that one of the words should not be modified because it's a dictionary word?
Okay, what the question is what if we have a dictionary operation? Why am I permitting you to delete a character from a word in a dictionary? Realize that there's an asymmetry involved, okay? Where if I type in, I'm trying to match a word to dog in the dictionary, okay? If I type DG, okay, what is that going to be, okay? You could think of this as being, to go from here to here, you could think of it as inserting an O, or you could think of it as deleting the O from the dictionary word. Okay? Likewise, suppose I want to match dog to D-O, let's say I have dog D-O-G-G, and I want to match that to dog. Let's say doog. Make it look more common. D-O-O-G. Here's my dictionary word. Okay? I could edit my dictionary word to insert an O, or I could edit my real word to delete the O. It's the same thing. They're inverse operations. Okay? But they're different operations. You can either think that I'm either adding and deleting from one, or adding to one and deleting from the other. It's sort of, there's different ways of thinking about it. Okay? But so what am I, okay, so any further questions about the recurrence relation? Okay, how many people think they see the recurrence relation? How many people don't think they see the recurrence relation? Okay, a few. Okay, let's look at the example, a more concrete example, and see what really should be happening. Okay, suppose, let's say, I'm trying to find where the word happy occurs in a particular string. Okay, what I'm going to want to do here is to keep track of what is the cost of editing my pattern string into my text string. For simplicity, let's just think about starting it from here. What's the cost of matching an H? This was going to be a happy. What's the cost of matching H with H? Well, it costs me nothing. But maybe I don't want to align the H with the H. Okay? It could be that I delete one character from my text. Okay? Okay? So to match, let's say, H, okay, how much does it cost to match HS with H? Well, my choices are that I could basically pay a deletion. I could delete this character and add 1 to the cost of matching the H to the H. Okay? Or I could, or I could do a substitute. Okay? Well, maybe that's not a good, an interesting part of the example. Let's say that I look at this cell here. This is probably the most interesting cell. Okay? What's the cost of editing HA to HS? Okay? There are 3 possibilities for what I could do. Okay? I could say HA is the same as, figure out what's the cost of matching an HA to an H, and then delete that S. Okay? I could do HA to HS, figure out what's the cost of editing H to H, and then pay the cost of my substitution. Okay? Or the other thing that I could do is figure out what's the cost of editing H to HS, and then pay the cost of adding an A to it. Correct? These are the three possible ways that I could somehow edit these first two sets of characters together. Is there anything else that I could do to bite off one character at the end? No. Which of these is going to be the best possibility? Well, it depends upon the cost of the thing in the parentheses. What's the cost of editing H to H? It's 0. So what's the cost of editing H to H and doing one substitution? 1 plus 0, or 1. What's the cost of editing HS to H? Okay, that's 1 because I have to delete the S, right? So what's the cost of inserting an A to the H after I've matched H to HS? 1 plus 1, or 2. What's the cost of comparing HA to H? Well, 1, plus the cost of then inserting an S. 1 plus 1, or 2. I am going to want to figure out what is the cheapest of the three possibilities. Okay? Which is going to be, in this case, do that match, and then add 1 for the substitution. Okay? Any questions about that? I see some puzzled looks. Okay? But basically what I'm doing here is going back to my recurrence relation. Okay? Where did I have this? Oh, right here. Okay? My claim was that there were three possibilities for what the three possibilities for what I could do to edit from the right at the last character. Okay? The cost of editing the first I characters to the first J characters is the cheapest of all the possibilities once I take off the last thing I did. And the last thing I did could have either been a substitution or a match, insert 1 to the pattern, delete 1 to the pattern. In all cases, I'm referring to something smaller, which meant that if I filled in my matrix right, it had to be there. Okay? And that gives me the right way to do it. Okay? Any questions about that? Okay? Question?
So your table will grow square-wise.
How will my table grow is a good question. Okay? If I think about it, I've got a matrix now. My table is going to be a matrix where I've got I and J here. Correct? Which cell is it that I'm going to need to look at in order to compute the value of ij? I'm going to need to look at I minus 1, J minus 1. Okay, because that corresponded to deleting 1 from here, from here. I could look at this one. That corresponds to deleting 1 from there. Or I could do a substitution, which means delete 1 from both of them, and either do a substitution or a match. So I'm going to fill in exactly, I need to have these cells in order to fill them in. Okay? How many people see that? How many people don't see that? Okay? How many people are no longer interested in raising their hands? Looks like we've got a lot of people who are in that state. Okay? What's the point? In order to compute d sub ij, we need to have d sub I minus 1, j. d sub I comma j minus 1 and d sub I minus 1, j minus 1. Those are exactly these cells. If I fill in my matrix like this, I know those 3 cells are sitting there waiting for me. Okay, so that gives me an evaluation order to do what has to be done. Okay? How much time does this take? How many cells are there to be filled in? Okay, if the string here is of length n, and this string is of length m, how many cells have to be filled in? N times m. How much work do I have to do per cell to fill it in? Okay, what am I doing at each cell? I am taking a look at two characters, comparing them. Is this the same or not? I am looking at this cell, and this cell, finding the minimum of 3 quantities. Takes constant time per cell. Okay? So how much time does this take? Okay? Order n times m times O of 1, order n times m time. Okay? Any questions? Okay? Okay, seriously, if there's any questions, I'd like to see the questions, because before I go on any deeper, this is something I'd like to see people.
Can you go back over that order?
Can I go back over the time order or the search order?
No, what you just said. It takes order.
Okay, think about what we've got here. We've got an array. Okay. Each element in the array, this is sort of the same picture that I was drawing before. We've got an array that has m cells by n cells. Each cell, I'm looking at 3 other cells and simply doing something. I've got order mn cells, m times n cells. I do a constant amount of work per cells. Order mn times order 1 is order mn. So mn time is the total time for doing this. Okay?
And the least path would be the root mn path, the diagonal path basically.
Okay? The cheapest path is going to be depending upon, so ultimately what we're going to get is a matrix like this. And the question is, we're going to then want to read through, starting from our cell, read back what was the cheapest possible path. In the case of happy to zappy, it would be a diagonal. But what about in the case of editing happy to HPPY? Okay? Then I would not be a diagonal. Because at some point, yes, the Y would match to a Y, the P would match to a P, the P would match to a P, but now I'm faced with matching an H to an HA. Why don't I just delete that A? That's going to be corresponding to going straight up, and then do the match. So the path through this matrix is going to be a function of which one of those 3 branches did I take at each point for the minimum. Okay? And then from that I can reconstruct what I was actually doing. Question?
So you have to store these decisions also to be exactly reconstructing the path?
Okay? So the question is, what is it that we actually return? Okay? If what we wanted to do was just figure out the cost of editing one string to the other, which in the case of the spelling checker is all that you would need, you don't need to do anything to reconstruct what the actual path was. You want to know that dog is a distance of 1, the DG is a distance of 1 from dog, and that's better than any other word in the dictionary. So it may be that you don't need anything else. But if, let's say, you want to actually figure out, hey, dummy, what were your misspellings? Okay, which in a lot of applications is important. You would want to reconstruct what was the actual path that you took through this matrix. Okay? And to do that, you've got 2 possible ways you can do it. Way 1 would be that we keep track at each cell in the matrix, which branch did we take next? And then work backwards, the way that we did with the other cell. Okay? Or if we want to be very clever, it turns out that actually, given this matrix, you can work backwards. Given the actual full values of the matrix, if you're clever, you can work backwards to figure out what the actual solution was. Because you knew that if you wanted to go to match happy to happy, it says you could do it in a cost of 1. How could you do it in a cost of 1 given these cells before it?
How do I know that I start with the 1 on the bottom, not with the 1 on the top?
Well, think about what the interpretation of this matrix is. This one down, this one over here, this is the pattern here. Remember? You want to completely match the pattern against, let's say, someplace in the text. The bottom row here corresponds to having completely matched the pattern.
Oh, okay.
This is the cost. What's the cost to completely match the pattern with nothing? Well, you have to sort of insert HAPPY, 5. What's the cost of matching this with a capital H? We have to do a substitution. Insert HAPPY, 5. Okay? Here, to match HA to that, you could do a substitution, HH, a match, and then insert APPY. So the cost of getting here would be 4.
Okay.
Once you're here, if you want to go back and reconstruct what were the patterns of things you did, you could simply reverse this. You know, to get here, you took the minimum of 3 possible ways. You could figure out which of those 3 possible ways were because you knew what you have the costs here that you used to base the decision. From here, you can work backwards to reconstruct what your decisions were in constant time per step. So in fact, there's no real need why you have to say the, if you want to reconstruct the path, you could in fact do it just from the numbers. Or to make life easier, you could actually explicitly say, hey, this is what I did, and store it. Question?
Ideally, you would have 0 over there if 2 words perfectly.
Right. If 2 words were perfectly matched, you would have a cost of 0. That's why the cost of editing here from little h to big H is a cost of 0. Okay?
And also your entire diagonal would be 0.
In an ideal world, your entire diagonal would be 0. Because you just did match, 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 match.
So can you also think of this as trying to perturb your diagonal from the ideal of 0?
Well, you're not, the question is, how do you think what's happening? The shape of your diagonal is telling you what you did to edit one to the other. Okay? You want the cheapest cost path to do it. Okay? Given the values of these matrices, that cheapest path is sort of becomes obvious. You don't have any control over that path. It depends upon what your strings are. They define the values in your matrix, and they define what the paths are. Okay? And you simply want to try to find that path that minimizes this cost.
No, but can't you start the other way also? Let's say, ideally it should be this. Why not perturb my diagonal and see if it matches?
Well, this is a simple way to do it. So, okay, you know, I don't know that you can do it that way. Okay, maybe you can, but I don't know that you can. Okay? Okay? Any questions about this? Question?
What's the initial pattern if I do a tax check?
If I do it, excuse me, the question is?
What's the initial pattern in the pattern tag?
You mean what are these? What are the boundary conditions?
Now, what's the initial pattern string we should have when I do a rare text?
When you're doing, let's say, a dictionary test, the word in the dictionary that you're testing is your pattern. The word from your text that you're looking for a misspelling would be your text. But realize that this is in some sense symmetrical. Because going from a pattern to a text, it's sort of in something, the cost of editing from A to B is the same as crossing from B to A. Wherever you did an insertion in one, you do a substitution in the other. So in some sense, it's symmetrical.
Yeah, my question is when I do a spell check on text, what's the initial pattern we should have?
The question is, when you're doing a spell check, how would you use this to build a spell checker? Okay? What you would do is, here is the word hazapi that you're trying to find the best possible match with. What you could do is first go through every word in the dictionary. For each one, try it as a possible pattern. Is A match with hazapi? No. Is AT a match with hazapi? Okay? And just simply go through every word in the dictionary and try the one that is minimized. Okay? There's actually a faster way to do that. Okay? But conceptually, that's what we're talking about doing when you're using this particular thing as in a spell checker. We're assuming that you're going to try all possible patterns against this. There's more advanced ways to avoid doing that. Okay? But I want right now people to focus on the edit distance computation. Okay? Any other questions? Okay? what's actually known here? There's a couple different things. Again, think about what it is we return. We're given the choice of, we're going to return the value of the matrix. Okay? If we return the value of the matrix, we can then reconstruct the path that we actually took in order to actually figure out what was the actual edit trace that we did. Okay? Or we could actually explicitly store what changes we made. One other tricky part about this recurrence relation is we want to think a little bit about what the boundary conditions are. In any recurrence relation, I mean, the guts of the recurrence are the expression where we do the substituting. Okay? But in fact, in order to get things right, we actually have to have a boundary condition. Okay? And getting the boundary right conditions can be a little tricky. What is the value of d sub 0 I, which I'm going to say corresponds to the cost of matching the first I characters in the pattern, text, with none of the characters in the pattern? Okay? How much should that actually cost? Okay?
I, because you have to delete them.
Well, if you want to compare a word in the dictionary, like let's say H-A-P-P-Y, with let's say, let's say, sort of, well, okay, okay, let's try X, Y, Z happy. I'm sorry. Okay? In this case, if you're trying to compare what's the cost of transforming this word into that word, you're right. You have to delete that ugliness at the beginning. Okay? And so the cost of doing that is the cost of the deletions. So if you're paying where you want to pay for that cost, where you really want to count that as a deletion, you should pay a cost of I. Okay? As was suggested. That's the case where you want to match one string into another string. Another option would be, and comes up fairly often, what if you want to match a string into a whole text and see where that string occurs? Let's say you're writing a program to scan for dirty words. Okay? You don't really want to know how close each word is to being dirty. Okay? You want to be able to edit. You have a whole text here and maybe a dirty word here. And you'd like to figure out where does this dirty word appear in the text. This is a substring matching instead of a string matching. If you were doing a substring matching, you would want to know, let's say that happy was a dirty word. Okay? You would not want to pay any cost for the words that were before it. Okay? So in that case, your initial condition would be a cost of 0. Okay? Because we're not going to pay any cost for deleting the first characters if we're doing substring matching. Okay? So think a little bit about that when you go through and think about these. Okay? Any questions about that? Okay? Question?
If we're just looking for a specific word.
If you're just looking for a particular word, you could do an exact string matching, and that would be faster. But let's say you're looking for misspelled variations of dirty words. Okay? So you're looking for people who are obscene and not good spellers at the same time. Okay? Then you would be doing substring. Substring matching is useful in a lot of other applications. The other point here is to see that what's the cost of editing dij, the first I characters of the pattern you want to match, against nothing of the text. Well, if you really want to match a pattern to the text, you can't say, well, delete everything, and that counts as a perfect match. So you do, in fact, pay for a cost of I when you do that. Okay? Any questions? Okay. One last thing for today. How much space? We said that this program took n squared time. How much space does it take to edit two strings together? Okay? How much space were we using in this recurrence relation? Okay?
We're using n times m.
We're using n times m space. Because for every character and every character and the text and every character in the pattern, we were finding what was the optimal way of editing into that. So we had an n by m matrix. If you're going to store that whole n by m matrix, okay, it takes order n times m space. N times m space is a bad thing. Okay, in practice, actually, n times n space is much worse than n times n time, because computers have more cycles to burn than they have memory to stuff things with. Okay? Is there a way we could evaluate that recurrence relation using less space? Question?
We could use 2n space. So we just keep the last column and the current column.
One observation is that you're right. Since we were only computing this thing by going from left to right, left to right, left to right, left to right, we were only depending on the previous 2 rows. If we wanted to save space, one thing we could do is, in fact, keep only 2 rows at the same time. Okay? Okay? Because once we have the values in this row and this row, we can compute this cell as we need it. So if you're clever, if you just want to compute the values of these cells, you could get away with order n space instead. Okay? But we said we needed to have order n times m space in order to reconstruct the actual path. Okay? So that's sort of a drawback of this. Okay?
Yeah, but if you store the path explicitly, then it's only order m.
Well, but you have to store all possibilities for this path. Okay? It turns out that actually there is a way. The thing that once you think about this a little bit, okay, it'll become clear that you could use order nm space and store all the paths. You could use order m space and just store the, and get away with just the value. Or you could use a super clever algorithm, which actually works recursively, okay, and actually gives you the actual thing in order nm space time and nm space. But that I don't want to go into. Okay? Bottom line, think about this thing. I realize this is a little hard and confusing. Sit down with the notes. Sit down with the book. Try to figure out these 2 recurrence correlations. The one for approximate matching and the one for matrix multiplication. If you didn't get it, come here with questions next time, and we'll talk about it then. Okay? Thanks a lot. See you then.